Thank you for coming to this IAS distinguished lecture by Professor Jason Ho, and it's uh, my great pleasure to introduce him to the audience. So Professor Jason Ho uh, is from Ohio State University, but he also holds a professorship in Tsinghua University in Beijing, and as we know, he is the one of the senior visiting fellow at our IAS at HKUST. He obtained his PhD from Cornell University, and then he joined the faculty of the Ohio State University in 1983, and currently he is a distinguished professor at Ohio State University. Sorry. He's the one of the leading theoretical physicists in condensed matter physics, and his interest is so broad, including the quantum fluid, quantum quasi-crystal, quantum Hall effects, and cold atomic gas. Especially his enormous contribution to cold atomic science is priceless and actually recognized by many different awards. One of them is in 2008, he was the recipient of the large Unsager Prize of the American Physical Society. And for example, most of the knowledge about the cold atomic physics, actually I learned from his important papers. That's one of the examples. And also he's the fellow of the APS, American Physical Society, and he's a fellow of John Simon Guggenheim Memorial Foundations, and many others. So today he will talk about his personal perspectives on the ultra-cold atomic science, and let's welcome Professor Jason Ho.
Well, thank you, Professor Joe, and it's my pleasure to visit HKUST again. It's one of the universities that has really spectacular, very lovely campus, and it's really glad to come back and see the old friends. When I tried to organize this talk, and when I tried several versions, one of the difficulty is that I think there are many people in the audience. They are in the field, and they probably have heard of what they're experts in this area. So one of the, on the other hand, the lecture is also supposed to be for the broader audience. So then one had to strike the balance. So the challenge is how to keep both communities interested. So I'm therefore trying to talk about things, hopefully that as many of you that have not heard them before. So I would first let's say, bring back a question that in the early days of co-atoms that many condensed matter physicists ask, which is that, well, I mean, well, what have you brought for us? So in order to do that, then I mean, I would try to answer those questions. So I would first give some backgrounds on the really quite spectacular success of this area, and then I would respond to those questions for the co-atom skeptics especially in the early days, with the following responses. But in particular, I mean, I like to talk about some success and also some serious challenge that we have. So I would just start with something light that which I just to maybe put a little twist in the current development, and then maybe one can also use co-atoms to achieve some kind of manifold that hard to achieve in solid-state physics. And then I would I'll come back quickly to address some very dead serious matter, which is many groups are stuck at some point, and then we need to find a solution. And I would not be able to tell you the solution now, but because they are still being studied and there's different philosophies. What I would like to tell you is different philosophies and different attempts to solve these problems. And then I would like to also address a mystery, which will it's a mystery of thermalization, which has been discussed in this workshop many times. And I would propose a different way of looking at it. Now, I should warn you that I may be saying some wrong things here, but I hope that it leads with generating some to stimulate some thoughts and some investigations, both theory and experiments. And finally, I'd like to talk about in some new directions. Or I think some promising way to get some correlated states, and I believe that among all the strongly correlated states or all the new state of matter that we are trying to get, I think, well, my guess is that we probably get the quantum Hall states in the closest near future. Now, so there are a lot of things to discuss in this menu, so I would not be able to go into some very detailed mathematics, but I would like to give you some favor. And I also, I think many people in the audience, many of my friends know that I have tendency to speak faster and faster. So I try to not do that. And let me see that I would still be able to do this by speaking slowly and do it within an hour. So first, let me see if I can use 10 minutes to describe some of the recent developments. It's quite extraordinary because now we have a lot of different capabilities. We can do a lot of things, make lots of things. We have lots of quote-unquote elementary particles to play with. These are the typical setup of co-atom experiments, and then the co-atoms are in here, and then they're trapped by lasers and sometimes by magnetic fields. And there is these are very, very, very dilute gases. It's 100,000 times thinner than air, and then even with millions times lower in density than in condensed matter. But then one can, so in order to see the quantum effects for such dilute gas, one have to go to very low temperatures so that the, oops, sorry, I'm supposed to put it in, I forgot. So basically, I need the thermal wavelength between the particles in order to be compared to in the particle distance. So when I cool down to such a, so the thermal wavelength grows as one lower in temperatures, and when it becomes comparable to in the particle distance, then one would have a quantum degenerate situation. The quantum mechanics becomes very important, and that's how the Bose-Einstein condensation was discovered. And as of now, this field is now a very special. Well, it becomes a branch of condensed matter physics and also atomic physics. The atomic physics, traditionally, they have a major conference in it's a DAMOP in the United States, and nowadays, I think in the last 5 years and or even 8 years, then 2/3 of DAMOPs is all about co-atoms. So it's really a major branch of atomic physics today. And also in the March meeting, they're getting a bigger and bigger representation every year in co-atom physics. And the field is also connected to all the different areas, which I would not be able to talk about. However, I would like to advertise that there will be a 2 to 3 month workshop at the Institute of Nuclear Studies at Seattle next year, and then is organized by the following people. And then some of you may not be familiar with Wu James Wise, and he is a high energy theory specialized in lattice gauge field theory, and there are now some ideas of using coatoms to do dynamic gauge fields, and then so that's and it would be certainly a component in the workshop to bring in some high energy physics aspects into the field, and now what started it all are these kind of things. I mean, these are around 2004, and I remember there was a workshop in Aspen, and suddenly some people show us a preprint from Munich where they did discover by now the very well-known mod and insulator, the superfluid insulator transitions in the Bose-Hybrid model. And what they did is that they have a three-dimensional. These are the lasers, and then lasers. If you put the lasers together, and each pair produce a sine wave, and then you have three sets of sine wave, and you form a lattice, and then the atoms either sit in the maximum or the lower minimum of the lattice, depending on the frequency of the laser, and then in that case, one can form a lattice, and then one can also tune the barrier of the lattice, and then therefore the particle can tunnel or not to tunnel, depending on the barrier, and when they tunnel, and they can form a superfluid for bosons, and they cannot tunnel, they form a mod phase, and then it was a great success, and the excitement is at that time is just that wow, we can make these things now, and we can see some of the models that the condensed matter people are interested in. But very quickly, one realized that has the potential to do all the other things, and that comes a few years later. And at the same time, actually a little bit earlier, and especially there's soon after. The discovery of of Bose-Einstein condensations, everyone wants to rotate them, and for the reason that because once you rotate them, and then somehow you can probe one of the most fundamental feature of the fluid, i.e. the phase and the vortex, and it was very, very hard. And then until I think at that time U.S. was beaten by Europe, because the U.S. tried several years, and then and once the European demonstrate how to do it, and then the MIT group produced a huge vortex lattice, so the interesting situation is that here we have a neutral fluid, and then it turns out that for neutral fluid, if we go, it's like on this is the Earth, and if you're in a non-inertial frame, something in the rotating frame, and there's a Coriolis force, and the Coriolis force acts exactly like the Lorentz force. So when you go this, and then if you just go on a straight path, and then somehow there's a force pushing you sideways. And so in the rotating frame, the neutral particle looks like electrons in the magnetic field. And now, on the other hand, for electron in magnetic field, when the electric field is very large, then we know that we will eventually reach the quantum Hall regime, and which is one of the profound developments in condensed matter physics ever. So there's also a lot of interest in trying to rotate a gas as much as possible. You pump in a lot of angular momentum as much as possible, and then so see what happens, and then we can get quantum Hall states. In the earlier days, that I tend to give the analogs that if someone drink enormous amount of wine, how many infinite amount of wine eventually becomes something else. So that's it's the question that if I pump in a lot of angular momentum into the fluid, then what would happen to it? And there's another aspect. It's called the Feshbach resonance, or changing interactions. Then let me not to do that. Let me not to go into that, except for something. But for mention the following: in the case of coatoms, there's a neat way to control interactions, and the process of controlling interactions corresponds to putting two fermions, and then they bind them together. In that case, then somehow the effective interaction during that process, the effective interaction of the fermions changes a great deal. Now, this is for coatom people, that seems to be very commonplace now. I mean, it's really remarkable. I can change interactions. But if you think about it, for electrons, it's impossible to do that because electrons are huge Coulomb interactions. You cannot bind two electrons together. It's very hard to bind two fermions together. In this situation, you can do that, and then that will give the coatom community a very powerful tool that's not available in electron physics to study a whole range of correlated systems, which I will come to later. The success of the optical-electrics experiments and the rotating experiments of in the United States, especially late, the Gila group has really rotated so fast at the system, which is so-called the lowest Landau level. And that has stimulated a major program in US, and that which have driven the activities for many years. And many in this audience were beneficiaries of that program. And then they were supported by this program for many years in the United States. And this program was originally, and then was proposed in the U.S. Congress to a very high level, and then bypass the usual path, and then it's going to the subcommittee that works for anti-terrorists. We'll just see how far high up it went to. And the goal was very ambitious. The goal is saying that they would want to produce a machine. That machine is so remarkable that if you don't know what this is, don't know what this machine is, like you put this thing in this machine and then you press a button, and then supposed to be in 24 hours it tells you they even named the 24 hours. The 24 hours tell you exactly what the equation of state and what the properties and then of the system, and that was the goal. And then in order to show that that goal was successful, then we need to test. To make some tests, so the first goal is to make this so-called two-dimensional anti-ferromagnet, and and all the condensed matter people know very well that this is a lot of speculation that this was related to high TC superconductivity. So and that which is still a mystery. So one would like to hopefully use this to explore some of the greatest mystery in modern days. Now, whether we are successful or not, we'll come to that very quickly. But during that process, a huge amount of developments, and then basically, as usually in science, you want to find A, you find actually X, Y, Z, and turns out X, Y, Z is either equally or even more interesting. And in fact, during this process, they want to find A, and they find X, Y, Z, and even not only X, Y, Z, and Gabi Bing Ding, and lots of things. And then this is the Gabi Bing Ding is Cantonese， 国语叫嘉悦丙丁是吧？好像是这样子。And these are all the topics that we have talked about in this workshop, and then there's a synthetic cage field that's huge. It's a huge development, and basically they try to. I mean, even systems are not charged, but you can really make them look through the nature and make them as if they're charged. And there's something called spin-orbit interaction. is a subject of great study of intense studies today. And then there are all kinds of new systems, and they have fascinating properties. I listed here because these are new systems, and then we have new techniques, and which I'll come to, and some of them are really very powerful technique to make all kinds of things. And then we also, apart from these techniques and systems, and there's also a very spectacular demonstration of the power of this kind of approach. And I will talk about all of them, except I won't be talking about very much about all these things because, again, not enough time. And then, but I would like to again emphasize that Dai Wei has organized a workshop in the IAS in China, in Beijing, in August. So these are the areas that would be discussed a lot in that workshop, and so I'm also advertising that workshop for him. He's sitting there. And now I would say a few words about the detection methods, and then because that again just to continue to demonstrate the power of these systems before I talk about, because I talk about some of the difficulties, and this is some of the pictures. This data by Chin Chen, and you take a picture of the cloud, and well, you may ask, so what? It turns out from picture like this actually can do a lot. It's not obvious, but what happens is that just by taking this picture, by processing it appropriately, you can actually know the equational state. What do you mean by know equation state? It means that we know all the thermodynamic properties. We know the density as a function of temperature and chemical potentials. All temperatures and all chemical potentials. So that is a very powerful, just by a picture like this. And this is another the further generations of detection method. And this is the so-called co-atom or quantum gas microscopes. And this is there's a way to produce images of such high spatial resolutions that you can actually see single atoms, and you can detect single atoms. You can address single atoms. Now, I say these three words. Each one of them actually has a very profound meanings. The fact that you can manipulate them, that means you can mix new things now, and then you can adjust them. That you can even go into. It's almost like the so-called Maxwell demon. You go in there and do some manipulation. Every atom by atoms, you can image them. That you can detect you can find out the quantum state of because in quantum mechanics, then quantum mechanics means that any operator you measure is the result of many times measurements. And here, so if you really want to produce the quantum mechanical results, then you can do these experiments many times. How many times? Maybe a couple of thousand times. And then it just takes very long. But Joe said, no, she's been doing it for, Joe Bong's doing it for a couple of days, may not be that long. You can take thousands of images. And then now, I would like to mention there's another new toy come into play, come into the scene, and this is is now being used by many groups now. Unfortunately, it's my fault that I haven't finished a slide. I want to demonstrate a particular aspects of this, but I'll try to say it in words. And this is the so-called digital mirror devices. Oh, this is not there. Then this this object consists of about 25,000 mirrors. Each mirror is something like this, can be controlled individually, and in each second, then it can change about 20,000 times. This is a very high frequency thing. So by shining light through this, and then you can produce using this as a mask, and you produce a pattern. And then now there are many groups that are going to produce a pattern, and you can produce all kinds of lattice now. Now, in other words, you don't need that many you only need one laser. You don't need 3 or 5 lasers. If you want to do two-dimensional experiments, you can just let the mask project onto the plane. And also, because it can change so fast, then you can actually, and you can write a computer program to change the pattern here. So you can actually move the pattern around and rotate the pattern. And that's all all possibles. Or you can do something like this. This, again, is my fault. I did not finish the view graph. So I asked you to imagine that suppose this one's not there. And originally, I have a sequence of wells. These are supposed to be harmonic wells. I'm supposed to cut it off. It's harmonic wells. So you think that all the atoms are occupying this so-called the lowest ground state level now. So everyone, I have an array of them. Everyone occupying ground state level, and this one's not there. Now it suddenly snap onto, just again, just instruct the mirror, press a button, change the computer program, and then you snap onto to a well like this. And this is a much deeper well, such that the second level or third level of this well matches more or less this level. So in this case, then you you suddenly let these atoms hop to another site and then back to another S level via a P level or other levels. In that case, then there are a lot more interesting band structure that one can construct, and that's another way to produce the so-called topological band structure. Okay, well, I think since times is getting short, so I'm going to just say that there are even more powerful methods that coming in the scene that are able to look at wave functions at even shorter scale, and there are algorithms. And then Jockey, I should like to thank Jockey. Take this opportunity to thank Jockey again for his work with me. Then I think I often said that we have walked in. He has accompanied me to walk a long journey in many areas in this field. So I'd like to thank you again. And then some of our method was used successfully in many for many groups. But finally, I'd like to show you a picture. This demonstrates the power of this approach. The power of this approach is that, as I say, all you do is take a picture of this object, and remarkably, there are ways to process this image. I mean, Jockey and I work a lot on those, and it is possible just from the image to deduce the equation states, and this is the equation of state of the so-called unitary Fermi gas. I mean, if you know it, it's good. You don't know it, doesn't matter. It's just some very interesting state. But they just look at the quality of data. This kind of quality of data is you only see usually in really traditional ultra-low temperature physics like helium physics. I mean, the error bar is so small. So here is the accuracy that we have now, and this data is so accurate that actually corrects some initial errors or some powerful Monte Carlo techniques. So so this is my introduction, and then to talk about the coatoms for those who are not in the field, and I hope you get a flavor of the excitement and success that one has in the field. Now, now I'm going to talk about the second part, that so again, back to the questions for the coatom skeptics. So, okay, any real surprises? And then, I mean, I was one of the enthusiasts that we can all kinds of things, but they say, well, it doesn't do me any good. But have you really, I mean, you set out to find the anti-ferromagnetic phase in 2 dimensions. Have you done it? Well, no. So, so what is the problem? Why are you not succeeding? So there's a problem. The problem is the heating, which I'll come to. But just before answering this, let's continue a little bit just to demonstrate that there are I mean, even though we cannot get to the correlated states, but maybe there's still something that we can do. But later on, we will address the problem of how to really address the most difficult problem, how to get to the correlated state. And in the correlated state, are there any new contributions that we can make to condensed matter? Right? So, so this is my first part of my second talk, and I want to tell you some relation between coatoms and biology. When you put the coatoms in non-trivial topology, and then something quite remarkable happened. And this is also related to some of the recent experiments in Amherst on the coatoms in to simulate monopole field. Imagine, so here's what I'm talking about. This is something that you're familiar with, that you go out to, I mean, this is Hong Kong tropical weather. You can see a lot of plants. And now, what's so special about this? And then let's talk about something called the Fibonacci number. It's very easy. It's a famous sequence and very easy to construct. You start with 0 and 1, and then you add the 2 and get 1, and you add the 2 successive numbers, get 2, and then 2 to 1, you get 3, so on and so forth. And this is the scheme is given by this. And if you look at all these plans, then typically the left gives the 2 set spirals, left spiral, right spirals, and they come together. And then in sunflowers, you also see something like this. And now I'm not going to count them, but you are very welcome to count them. And I bet money that I hope you bet against me, that the ratio between the Fibonacci numbers, so either 5 or 3 or 8 or 5 is 8 or 13 or 18, etc. You don't get 18 to 5 or 18 to 7, something like that. Now and then there turns out there is a reason for something like this, and this is a typical situation of growing a crystal on a cylinder, on something that has a hole in it. Now, why that's the case, let's not go into that, but if you grow something on a cylinder, then you will tend to get the Fibonacci sequence. Now, here I'm suggesting that there might be a way to do this, but it turns out the way is actually not, the reason is not actually to simulate this, but the reason is actually to generate a so-called Landau gauge, which theoretically is very interesting. But a spin-off is that you can actually relate to things like this. Now, and so we have let's say, suppose we have how do you generate a cylinder? Let's suppose you start with a cloud. Say in a trap, and then you put in a blue laser to punch out in the interior, and then so the whole thing becomes an annulus. And now you do the following as the UMass Amherst group did, and then you put in a quadrupolar field, and then the quadrupolar field has a field structure like this. And the field is large, and then also the zeros are here. So outside in this region, the field is large. I mean, the quadrupolar field is linear depending on x. X is the distance from the center. So this field is large, and then so you line up the spin. You only look at the spin that's parallel to it, and then again for quantum people, that this is how the magnetic trap works. And then so if you only work with this component, and then you get the effective Hamiltonian, and you get the gauge field and the gauge field, and then you work out the gauge field, and the answer turns out to be, and so it turns out to be a Landau gauge. I mean, if you look at them, and then one can show that the gauge field that one come out is like this. That the Landau gauge has, so he look exactly, and this come from this Barry's phase term, and S is the strength of the is the magnitude of the spin. So the larger the spin, the better, the bigger the magnetic field, and then so it looks like a Landau Hamiltonian, and then if you put BC on it, and then gradually they will arrange in a lattice, and then this is the so that's an analog for, and then you can likewise. I mean, you can punch. I mean, suppose in endogenous experiments, and then they were with 2 different species, and I know this is not easy geometry. I mean, as I say, this is for fun. But suppose you have 2 species that are repelling each other, and then one's going to the surface, and then this is in another species. But then again, you put in a quadrupolar field, and then again you work out the Barry's phase, and then therefore you have an effective field that again becomes radial, and then now you can again put BC on it, and then you would have a interesting pattern, and then also of course that if you have fewer atoms here, eventually you can go to some quantum Hall-like regime, but that would be difficult, I mean, for various reasons. So now I'm going to go to another part, which is that the part is that why are we not succeeding in getting into the Ntype ferroelectric phase? It has been 5 years, more than 5 years. And it is the original goal of the DARPA program. And it's very fortunate that DARPA did not emphasize that aspects, but still continue to fund all of us. That at that time, the problem turns out to has something to do with the cooling, and then I'll explain the difficulty of that, and then I will talk about different philosophy in the approach. I mean that, and then Peter Zola and I have been. And his group and I has been having discussions, and it's a very interesting and friendly disagreement. And then I think that as a result, that many, I think, good studies come out. And then I'll talk about another scheme which proposed by the quantum optics community, which so here's the problem. The problem is that. The problem is the following, that let's remember, or let's first re-examine how we cool things at the last stage in all these experiments. And it is through the so-called evaporative cooling. The evaporative cooling is very, very neat things, and it really makes use of the atomic structures. For alkali atoms, it has spins, and then it spins, and when you see a magnetic field, and then the level has a Zeeman split, and then and then you look at the Zeeman term, and then you expand it you expand it with respect to the angular momentum state. Then it looks something like this. Now, if this field has a linear dependence, which is like the quadrupolar field that we see as a linear dependence. So as you go away, then the field gets bigger, and therefore the energy increases. So as a function of R, so this is actually a attractive a well, and this is the confining well, and this one doesn't have the M goes zero state would have no potential. So what is trapped are those states up all these states. They are trapped. The more energetic states are trapped. These states will go out from the trap. They're so-called low field seeking. They just keep going farther and farther away from the center. And this one hang around the center. Now, so therefore, suppose you have a cloud like this, and then if you just come in with the RF, with the radio frequency, and then just flip the spin from here to there, and then you can get rid of these particles. And then if you change the frequency, go from one frequency to the other frequency, go this, and then you can just cut off this shell. So you can actually, that's what they call the RF knife, that you can just cut as much as you want, and then you can cut precisely where you are. And then once you cut it, and then you cut off all the energetic atoms, and that's very good for cooling. These are energetic atoms. And now, however, when you put it on a trap, suppose you have a large optical trap like this, and there's a difficulties because now the optical trap typically is much stronger than the magnetic than this Zeeman energy. Now you can and then now you can flip the spin. You can flip as much as you like. It doesn't do you any good. So therefore, you're still trapped. And so that is the problem. And so the way to solve the problem traditionally at the moment is something that中文叫什么？中文叫无可奈何内何。Just somehow you cannot do anything, and then you just that's the best you can do basically. And so basically, the one just produce a gas as cold as possible, and then you turn on the lattice, and then hope that during this process is adiabatic. So therefore, the entropy of this system doesn't change, and you as you raise the lattice. So basically, all the entropy, I mean, all the process lowering the entropy is at the beginning stage, and then once you start turning on the lattice, that there are no more cooling power, and therefore that is a source of difficulty. Basically, all the cooling power, if you want to cool the systems, and that's where you are. Once you start deciding to do the experiment, turn on the lattice, and then you are dead. And if in during this process, there are more and more mechanisms to introduce entropy, then the system is hotter and hotter than one thought. So at the moment, the reason we get stuck is that there are many reasons. There may be heat coming in during the process, and we may not be able to cool this enough. So what is really needed is to find a way to continuously cool the system, to pull out entropy during this process. After the lattice raise, then you still have a way to pull it out, and that is a challenge, and that is being studied and worked on by many groups. And well, this. Jockey and I have worked quite a bit on this. Now, but then I would like to just chat a little bit about the difference in approach between the quantum optics group and the condensed matter group. The quantum optics group has traditionally had the approach of trying to identify problems. So, see where the heat comes from. I fix it, and if there's a leak here, on the cure this problem, here's cure this problem, and so the hope is that if I fix enough problems, the system, you can cool the system, and the condensed matter approach is which is I think mostly advocated by Ohio, is that I would advocate that you ignore all the leaks. Do not even bother. Well, of course, the big leaks you need to ignore. Otherwise, with so many of them, you can never finish. Because why? Because we have the experience of helium-4. I mean, helium-4, if you do experiment up to this day, there are all kinds of leaks. Even up to this day, that you cannot figure it out. And that's why the supersolid experiment is so difficult. That they are things that you don't know where the heck they come from. But on the other hand, that we were very successful in getting to very cold temperatures, like the helium-3, the superfluid. The reason we get helium-3 superfluid is because we have an extremely powerful cooling technique. The cooling technique is extremely simple. It's called Polymer charge cooling. What does it do? You just do this. You have a solid, you want to cool it, just squeeze it, that's it. You don't need to do anything. You don't need to plug any leaks, and then the cooling power is so strong that you then it overtake all the leaks, and that is the approach that. So I think what one needs to do would be to look for clever ways to have a powerful to have a cool strong cooling power, and now there's however. Another view is say, well, let's not do anything. Let's make them. What do you mean? Because remember, early on, we say that now we have very powerful techniques. We can put atoms together. You can put it one by one, and then like the like the co-atom microscope, let's join them together, and then therefore, for example, if I want to make an anti-ferromagnet, then I can just first make a anti-ferromagnet, make it on an array. Suppose I can make this pattern. And the fact that I do not draw a line here, that means every site is completely disconnected. And this one, let's say maybe this one is in one room, this is in Hong Kong, and this is one in Boston, and this one in Mars, and something like that. So everywhere. So every one of them you can be sure you're in the ground state. And then now I'm going to turn on and bring them together from different planets and put them together gradually. And then eventually I bring them close together. And then if the process is adiabatic, the zero entropy state and zero entropy state. And then provided the system is adiabatic, the system can always go from zero entropy to zero entropy state by definition. So why bother to cool it? I mean, just put it together. And then there are efforts to do that. And then they were able to make double well and then maybe a string of something. And then, for example, there are efforts to make a so-called RVB state by first produce a singlet of this object, and then try to join them together. And they were able to, I mean, there are a lot of many science and nature experiments on this, and they are, but I would say that none of them, I mean, they were able to see all this order for small clusters, but then when the cluster get big, anything that's close to condensed matter, you do not get it. And let me just give, for the co-atom experimentalists in the audience, I would like to even, that's something that I told Wolfgang in the latest meeting. Look, I mean, you do this for bosons. You take this is a mud insulator. Again, you can produce mud insulator with no hole. One chunk of them. You lower the barrier. See whether you can get T equals 0. T equals 0 superfluid. All the superfluid state we have at the moment is about 10 to the minus 6 to 10 minus 9 degrees. You cannot get lower than that. If one can even get to 10 to the minus 11, 10 to the minus 14, that is a huge success. It makes history of science. And why can't we just even do that for the ordinary good old Bose liquid, the Bose gas? So the reason is, I mean, I claim that this cannot be done, and I would not be able to go through the mathematics. And then the key is the following: when you go through this process, because if you have started with something that's disconnected, and then you begin to connect them, and there's a process, because then you allow the particle to tunnel now, and then the tunneling go from really absolutely zero to some finite value, and you are inevitable to go through a region where your noise dominate over your tunneling. So there's a period before you get to the really adiabatic process. There's a period the tunneling is noisy, and then during that period, the system would introduce the entropy. So, but I just want to point out the fact that one does not have to, for example, believe me what I do. Just the question whether one can settle the issue experimentally is that if you just do the best adiabatic process one can and control the noise and in some systematic way to see what is the limit that one can get. So I just want to point out that what is allowed theoretically, in this case, that if you really assume everything can be adiabatic, and sometimes may not be realized in nature. I mean, we know very well in elementary textbooks in high school and then to teach the mathematics and draw a circle. Here's a circle. Here's a cylinder. I mean, in reality, there's no such thing in the world. There's no cylinder. There's no because if you go into anything that you think is smooth and you go to the microscopic detail, there are atoms. I mean, there's no such thing as a really perfect sphere. And then so the other example is a Schrödinger cat state. I mean, we think that, well, in principle, you can add a Schrödinger cat state, and then but this state has a problem. This state is that if you try to disturb it with any small disturbance, this can be 10 to the minus 20. And then this one says that if you detect one particle, you localize the system in this state. If this state is 10 to 22, so even you put something is 10 to the minus 20 or 10 to the minus 30, then immediately you localize the system in this state. So that's why the Schrödinger's cat state can only be found for for maybe at most 100 atoms. I think that the largest micro cat is about 100. So this is I for myself, I'm very skeptical of trying to produce an antiferromagnetic state to put things together. My view is that one have to bite the bullet and you have to cool. Finally, well, let's see. I have 10 minutes. Let me see. I can. Well, okay. Well, I have 10 minutes. No, I'm just joking. So I have two more area to. So now I'm going to address a different issue. This issue wasn't paid attention to for a long time because people say, it works. It's just academic. But now because of works like Andre and then there are other works, and that we now have more theoretical, precise work, and we know, and also there are ways to explore things experimentally. So this becomes a important problem now. And the problem actually go into the foundation of thermodynamics, how the system thermalize. And we know, I mean, again, we are told again and again that if something evolve unitarily, it would not thermalize. But in coatoms, then it's a very annoying. It could be an annoying counterexample because once I do it, let's say suppose I do evaporation. I mean, suppose I start with something, I just use RF knife to cut it somewhere. So the system is in some quantum state, or maybe even be in some ensemble. If you do many experiments, then you let it evolve. But then somehow the system says that because experiment after experiment says the system thermalized in no time. Almost every time you can, then it thermalized. But then the quantum mechanics say that it seems to be contradictory with what one expects. So coatoms is a thermal equilibrium state that should not be, but then it's there. And now, So I would like to put, now this is the part that I say that I think there may be, I mean, Domenico may be jumping up and down and will kick me at some point. Where's Domenico? So I may be something crazy, but it's okay, it's among friends. So let's consider one particle in a box. So we know how to solve the problem. The problem is, sorry, I don't write in simple notations, is the wave function is e to ikx. V here is x, okay? Why I write 2 pi I, it's just write 2 pi. So I took it from the other talk, but so it's e to ikx. And suppose I start with delta function of e to ikx, and then, so this term is not there, and there's delta function. And then now I evolve it with time. So, but the energy is k squared. Now, and then because k is 2 pi over L, so I can just shuffle all those constants into these numbers. So this k is now integers. So because k is 2 pi divided by L times n. So I can, so this is now so basically for particle in a box, and then I just initially its delta function is like this, and this is and for the mathematicians, they know that this is a theta function, and the theta function has many surprising properties. And then for the string theories, they will tell you that they know very well. And then the theta function has amazing properties. That means that even a particle in a box, its propagation has amazing properties. And here's a book at the preface of the book, which struck me is when I first was introduced to the theta functions, and theta function is a branch of elliptic functions, and it says that it talks about a curse of all the mathematicians. Say of all the mathematicians that the elliptic functions, the fairylands of the mathematics, the mathematicians who once gaze upon them, this enchanting and wondrous domain, crowded with the most beautiful relations and concepts, is forever captivated. Now, many of us are, well, myself is not a mathematician. However, it is this, I have to say that this is quite captivating. So let's look at the propagation of a wave function. So here's how they propagate, and t is roughly time, and then here's these are different times at different times. It just shows at different times, and things there seems a regular pattern. However, if you just look at more continuously, the time is quite different. It's so the whole thing is and now you can see it. Sometimes it becomes messy. Sometimes it becomes more quote unquote coherent. And these are the patterns as one goes down, and these are all can continue. These are all the patterns, and then. So this now, and then if you display the whole thing, that one say this would be time and this would be space. I mean, and then the bright areas corresponds to the location of the particles. Then you can see that every now and then the bright areas occur only every now and then. Now you say, what does this have to do with thermalization? Now again, we have said that there's nothing. The world is nothing perfect. I mean, to me, there are always noise. I mean, like in Schrödinger cat, there's also noise that would destroy Schrödinger cat. Well, ladies and gentlemen, please do not misunderstand. I say that this phenomenon is driven by noise. Like, for example, in the case of Schrödinger cat, it doesn't matter how much noise you have. Sometimes your noise is very small. As long as the noise exists, then your cat is dead. So it doesn't matter. So I'm not saying that the phenomenon is driven by the magnitude of the noise, but the phenomenon is driven by the existence of the noise. So here, suppose you imagine that every now and then you have a noise. Then you once a noise, and you basically mix all the states and you restart somewhere. And since the bright area is only occurs very rarely, so therefore if you have some noise, then you would basically the bright area may not appear as often. In addition, I mean we haven't talked about the interactions. Turns out, at least for two particles, because two particles, you can also write the two particle wave function as in its propagation with interactions as a product of theta functions. Again, you can see, but in this one will be periodic bound conditions, and then one can see basically the chance when it becomes coherent becomes less and less. So this could be, I mean, because if it's not coherent and then you look at density profile more or less flat, so I think the noise, the existence of noise may have a may have some effects, may play some important roles in the thermalization issue. Now let me come to the very last part of my talk. I mean, even I was given an hour and a half, but I don't think one's supposed to use an hour and a half. This go to the another the aspect of the heart of the matter, because all the current effort is to really to make some state, some very novel state, and not only that, we'd like to learn something we haven't learned before. So I would like to propose a way to get to the quantum Hall states, and then and there are now quite intense efforts in various groups. Especially and then in Chile and Harvard, to look at the to look at these states. And I would just first I give a very simple example. Just to demonstrate that some even by doing something very simple, one can actually explore some rather interesting effects, which would be of interest to condensed matter. The first thing I would like to say is how to further split the fractional charge into pieces, and basically perhaps. So we want to see what the internal structure of the quarks now. So here it's very well known. I mean, even though you don't know quantum Hall effect or Landau wave functions, it doesn't matter. And then the you only need to know statistics. The statistics for bosons is even, and these are location of the particles on the plane and in complex coordinates. And then the bosons is Zi minus square. Suppose that is the wave function that will make the interaction vanish. And it's obey both statistics. And here is a wave function that will make the interaction vanish, but it's Fermi statistics. So this is fermions and bosons. Now what happens is that if you put this in, this is what happens when you put it in a trap. But then you squeeze the trap, and turns out this is what you can find. Then this one, if you squeeze trap in this direction, and then the zeros actually splits. And the reason zero split is that on one hand, they want to minimize the energy, but also you need to minimize the potential, the potential energy come from the trap, and then basically in some way is that your metric is that the space or metric space that you're living in is deformed, and the system need to accommodate with that deformation, and then so and then for the case of fermions, and then it will split like so, and that also give you one as a chance about this. I have not yet figured out how to do, but if one could actually have another quasi-particle can move around basically say move a loop around here, then you can begin to see the internal structure of the original fractional charge, which are not easy to see. Typically, one thing that there's no structure at all, it's just they all collapse into one place, but turns out it's not. You can actually resolve the internal structure by changing the metric. Now, but then this is but the next thing I want to talk about is a more serious matter, and it's what I consider is really a co-atom magic, with a new contribution to quantum Hall physics. First of all, the first point I want to make is that there's a lot of effort in making quantum Hall states, and they use bosons, but actually it's easier to do fermions, and for a very simple reason, for the reasons of statistics. For bosons, in the case of rotating gas, we are very fast rotating. The energy level is first worked out by Landau in this amazing paper. Is that remarkably the energy level form levels, and they are more or less degenerate. I mean, for the cold gas, and there's some slope here depending on but for the cold gas, then typically there's an energy level. Now, for bosons, they like to both condense. But the quantum Hall state turns out, I mean, again, I don't have time to go into details. For quantum Hall state, in order to achieve the quantum Hall state, one needs to spread out all these occupations. The quantum, and this is the quantum Hall state. Now, so the quantum Hall state fights strongly against the both statistics, and then the boson is not a very good a particle for looking at quantum Hall states. Now, on the other hand, you have fermions. Different. The fermion automatically, they don't sit on top of one another. They have to be in different states. So fermion would naturally spread out. You don't even need interactions to spread out. In the case of bosons, what happened is the following. In the case of bosons, is that all the bosons would like to sit in this state, but if all the bosons sit in this state, then all the bosons have the same wave function. And same wave function means a lot of interaction energies, they are repulsive. So the repulsion like to spread them out. But then on the other hand, both statistics like to bring them in. And then so in order to spread them out, so basically one need to make this level flatter and flatter. And then, so when it's really flat, then there's not much energy to spread out. However, if this energy level is not flat, then when you spread out more, then you get more and more energy. And now you say, okay, wow, what's the problem making a level flat? It turns out there's a problem experimentally. Then one can control this slope just by controlling some rotating frequencies. But if you can make it flatter and flatter, sometimes you can go down here, and there's a whole thing just fall apart. So therefore, there's a technical difficulties of producing the quantum, make it very flat, and that is the bottleneck for making quantum Hall states for almost a decade now. But for fermions, then you can actually make it. Suppose you can construct quantum Hall state easier, and then our efforts to begin to do that. Now, I would, however, say that once you make the fermionic quantum Hall states, then you can actually make the bosonic quantum Hall states by using what I call the coatom magic, which I mentioned to you earlier when I talked about Feshbach resonance. This is the only thing that you can do in coatoms, but not in electrons. In electrons, you cannot bring two electrons come together. For coatoms, you can bring two fermions together. For example, you have two spin up and spin down, and the experts in the audience know that the wave function of spin up particles in a few Landau level is just Zi minus Zj, and I call it A or Ai minus Aj. And then for the lowest Landau, for the second one, spin down is Bi minus Bj. Now, the Feshbach resonance said I bring the two particles close together. Let's say, suppose I really bring them together as if they're point particles. Then you become something like this. And this is a Loveland state, a bosonic Loveland state. So by going through a Feshbach resonance, you can go from one to the other ones. Now, what happens if you have two Landau levels? Now, okay, this is a little bit busy, so don't worry about it. Let's look at the two Landau level. Just forget about this guy and forget about this part. Just look at the A's only, okay? If you have two Landau levels, turns out you can write the wave function two Landau level as the following. You divide the particles into two groups, from 1 to n, from n plus 1 to 2n, two groups. One of them form a Loveland state. This one form another Loveland state, but then to tell the system is in the lowest Landau level, when you're in the second Landau level, you need to multiply A star, and that's all there is. And this is for spin up, and then you do the same for spin down, which I call B. Now you do the same trick. You make A equals to B, and there are many ways to make it. It turns out end up to be the same, and then then you get a factor, Loveland factor for the first group, a Loveland factor for the second group, and then some junk. And then this turns out later on, we say the so-called quasi-particles, but at the moment we don't need to worry about it. So this is so the first group becomes the Landau level, second group goes Landau level. Now it turns out there is a remarkable identity by Cauchy. The Cauchy saying that if you have the product like this, then it becomes like this. And then how to prove this? And then it turns out it's not difficult, but the meaning of this is that you have two lowest Landau level multiplied together, then apart from this factor, and it looks like this determinant means that the two particles are paired together in this form, and this is the p-wave pairing with the two particles. And then now, if you take this, and then you discover that this is a, because you use a Cauchy identity, and then you discover then this state is precisely this, and this turns out to be the so-called Farfian state, and that it is apart from this factor, which is completely anti-symmetric for all the particles, and then all the particles are pairing in a p-wave pairing. So the message is that if you take two fully filled Landau level, you pair them together, and I mean, you go through fresh Bach resonance, and you will get the Loveland state. If you take two levels, and you get the and then you'll get the Farfian states, and then of course now you can begin to take one full Landau level here, the other two Landau level, the other one. So there are many choices, and one can make different types of states. I think this is the I reached the end of my lecture, and so let me just bring back to just give me a minute. So since I did not write the concluding remarks, so I'd like to bring back the first slide that I'd like to. Sorry about that. Yeah, and so I think that we do have a chance to contribute to at some fundamental levels to not only condensed metaphysics but to physics. And for example, if we can really further make progress in understanding the issue of thermalization and perform experiments that to really understand to dissect exactly what factors that would control the thermalizations. I think that would be a great progress to physics in general. And then there are some aspects of these topological methods which I think is very, the coatoms can be of very of great use. There's a way to really further into the look into the further structure of the fractional charges. But I think what the coatom example shows is that there is, for any fractional quantum Hall states, a billion on a billion, there is a parton model. That's actually something that one can actually, I mean, for all the bosonic states, you can actually split them into the fermions, and there is another level of internal structure for all the quantum Hall states, and turns out in this case it has a practical use. And of course, if we can solve this problem of how to, and I believe that if it ever works, I mean, like all the methods in coatoms, if it ever works, would be very, very simple. And then I hope that soon, before I retire, there will be some history of science that will be made, i.e. we can go to 10 to the minus 14 degrees. And then that would be really wonderful. And of course, wow, this is just fun. Thank you.
Okay, well, I'll be noisy. So I like the noise thing. And the reason is, I agree that there's always some. And I think that's fundamental because it's the reason that everything isn't just smooth, right? If there was an initial singularity that disrupted and everything were perfect, then there wouldn't be any non-uniformity in the universe and nothing would be going on. It'd just be a lot of smooth energy. So do you think that there's like always enough noise that all individual universes are going to be non-uniform?
I do not know. I haven't studied cosmology as.
Oh, well, I don't know either.
But I think that, I mean, as a matter of reality, I mean, for all macroscopic systems, there are always noise. I mean, I guess the aspect I want to emphasize, there are noise and noise. I think the aspect I emphasize is not some some event that is driven by the magnitude of the noise, I want to emphasize that those events that are driven by only the existence but not the magnitude of the noise.
Okay, thank you. We can talk more about that afterwards.
Yeah, I have a question about the thermalization part.
Yes.
So what did you do? You took a particle in a box and
Yes.
then you let it evolve,
Yes.
and then you observe these it's kind of a collapse revival patterns. Or
Oh,
something
you would
like
have survival.
Yeah.
You have a revival time.
Right,
Revival
right.
time will get longer and longer if the box gets bigger and bigger. So yeah, but there are lots of things happen between the revival just within one cycle. That's what I'm trying to say.
Right, right. And so you were suggesting that when people observe these kinds of thermalized states, they might just be those states in between? Or
No. I guess of course, this is a very simplistic example, but I want to demonstrate in this example that even for a single particle, the propagation is already quite complex. And for real systems, that's the reason I mentioned two particles, because then one can begin to see the increase of complexity. Because for two particle system, you can still do the same thing, but fully interacting.
Fully interacting.
Yeah, fully interacting. And but to be sure, you would have revival also. But then my prediction is that the more particle you have, the occurrence of coherence would decrease, because here you can see every now and then there are times. In fact, there's a regular times given by some rational numbers that system can revive. But I think that the situation would get more and more rare, and because they're more and more rare, so therefore by the introduction of noise, however small, will further make them even more rare. I mean, if the occurrence of, let's say, the first, even I eliminate all the coherent revival, then the system may not be thermal, but at least that I need to eliminate them first, because otherwise it would definitely not thermal. So, but then I would suspect that they can be, eliminated very fast. Like I said, this is my conjecture. You can, well, since both of us are in Tsinghua, maybe I think I'd love to chat more about this, because I only have conjecture. But as I say, this is that is the part that to talk among friends, that talk to there's a flowing out of some ideas as well.
Okay.
Any other questions? Then I have just questions. So you mentioned the two different philosophy in the cooling.
Say again?
Do you have two different philosophy on the cooling the atoms? Do you have any comments on the other approach, the condensed matter physics point of view?
The condensed matter, but I think there are. Well, we have I think we have number of schemes, and I think the key would be try to find a ways to evaporate while the lattice is on. And I think now we begin to see there are, Jockey before and I have we propose some dimple trap, some very, well, I think the principle that usually if you do adiabatic expansions, that always cools. That's a principle. And the question is whether it's something that is even better and more active. And I think now, because of all these new lattices, and I think some idea is to join different, just to basically you design the lattice so that you can allow some heat to leak out in certain directions. I think Randy has performed that with some success. And then his latest way of cooling it used part of those. But I think it is definitely not optimized, because there's one step which is very crucial, which he hasn't implemented, which is that when you, what happens is that when you begin to evaporate loose particles, your chemical potential also rises, because, well, also decreases. So what happens is that then as your temperature cools, your TF also lower. So your T over TF remains more or less constant. So what happens is that one have to, when you cool, when your temperature drops, you have to maintain TF. That means you also have to compress so I think we still believe the dimple trap, and then perhaps a clever way of leaking out the heat would be possibility. But I think there are other groups too. When there's a new preprint, I have to look at it from Anton George's group, and they may have some new ideas. So I have to see.
Thank you.
But he also uses the condensed matter idea, so Peltier cooling, something like that. Jockey is supposed to tell me what it is.
On your cooling effect,
Yeah.
is there a size effect? By that what I mean, if you start off, I understand your samples when you do the experiment on the order of 100 microns.
Cooling, yeah, it does depend on size. Yeah, I mean, if you have a very small system, then cooling is not a problem at all. I mean,
right.
you can put the system in the ground
So
state.
when you have a large system, you have this problem.
Yeah. Basically, the rule is that if you have the larger system, then it's more likely that you have degenerate modes. I mean, so basically, when we near the ground state, we have more and more modes that are more degenerate, then the system is less likely to be adiabatic during the process, and that is a killer. Whenever the system is not adiabatic, then it introduces there's a way.
So less than 1 micron systems, whatever there's no.
I haven't done it, but yeah. So the smaller the better. Yeah.
Well, that's a quantum effect. That's what you would expect.
Yeah, you go down to a single well, you would not have. But the goal is not to go to a single well. I mean, here we want a big chunk of thing to cool. I mean,
Okay. Any other questions? If not, let's thank Professor Ho again.